Okay, so we said we are going to find current I. So let me re-add current I to our picture. And I chose to be contrary. I chose to say current I is going in that direction. And then let's see, I think I said current 1 is going up. So current 1 is going like this, and current 2 is going like this. We want to find current 1 or current I. There's a couple of different ways that we could find current I, but what I'm going to do is I'm going to choose a loop that has current I in it. So that's the loop, that's loop 1. Loop 1, I'm going to start off from point A, and I'm going to find the potential difference from A to A going through loop 1. So when we look through loop 1, and let me just redraw loop 1 alone right here. So here's loop 1, here's our EMF, here's our resistor. We have point A here, we have point B here, we have this current here, this current, oops, and we set the current is going in this direction. That is I. And then we have I1 going up, and loop 1, we are going in this direction. So let's do Kirchhoff's law for voltage on loop 1. I'll start off at point A, and we are going to go to point B. So this is the potential difference from, this is going to be fun. Yeah, the potential difference from A to B, that's going to take us across our power supply. And then this will be plus the potential difference from B back to A. Well, the potential difference from A to B, well, look at that. That's going across our battery. And that along that path goes from the negative terminal of the battery to the positive terminal of the battery. So that potential difference from A to B is equal to positive the EMF of the battery, going from the negative terminal to the positive terminal. So we made our way, and actually let's just do this piecemeal. So we made our way across the battery. That was A to B. Now we have to go across resistor 1. So in going across resistor 1, that is the potential from B to A. And I'll just indicate our resistor, point B, point A. Now in here, we are analyzing from B to A, but notice the current is from A to B. So here, because the current is opposite the direction of our analysis, we would say the potential difference across the resistor from B to A is a positive IR1. So now if we do Kirchhoff's law for voltage, remember it's the voltage from A to A in our complete loop is the voltage from A to B plus the potential difference from B to A. We know that this is the EMF of the battery plus the product of the current. And I should have put a subscript 1 for the current through resistor 1. So the current through resistor 1 times the resistance of resistor 1. And since it's a complete loop, that must sum to 0. So notice what this equation gives us. This equation doesn't give us current I, but it gives us current I1. Because we know the EMF of our power supply, we said our power supply has an EMF of 9 volts. We said resistor 1 is a 3 ohm resistor. We said resistor 2 is a 6 ohm resistor, which I'll just call twice resistor 1. So this gives us the current being equal, oh, look at this. The current is equal to minus the EMF times the resistance of resistor 1. Look at that minus sign. Well, what this means is the magnitude of our current is equal to the EMF of our power supply by the resistance of resistor 1. Since both of those are positive values, but we have a negative sign in front, what that means is the actual direction of the current through resistor 1 is opposite the direction I assumed. I assumed the current is going up, but in actuality, the current is going down with the magnitude equal to the ratio of the EMF of the battery to the resistance of resistor 1. Okay, so I assumed the wrong direction, but that's okay because I know how to interpret the minus sign. The minus sign means opposite your assumed direction. So we now have an expression for the current through current 1. Now I'm not going to plug this into anything just yet, because now we still need to try and find the current I that is in the branch of our battery, and we have another loop to choose. Okay, and we're probably only about 5 more minutes away from finishing this, if you're wondering how much longer. Not too far, 10 at the most, probably 5. Any questions right now? Okay, so let's go ahead, and again, our goal is to find that current I, which we have going down. We know the direction of current I1 now, and well, I guess since we're going to stay consistent with our original problem, so I'll still just put I1 like this, even though we know it's actually opposite the direction. Algebraically, I'm going to stay consistent, and it's going to work out just fine, and you'll see. And then we have I2 coming like this. So let's now look at Kirchhoff's law for voltage for loop 2. Let's see, which direction did we say we were going to analyze? Okay, we were going to analyze loop 2 in the clockwise direction. So what that means is, analyzing it in the clockwise direction, we're going to do the potential difference from A to B, and then we got to do the potential difference from B back to A. The potential difference from A to B, well, notice, and I'm going to stick with our original assumptions. So notice, from A to B, our analysis path is to the right, and the current goes from A to B. Since we are analyzing in the direction of the current, the potential difference from A to B is actually minus I1 R1 for this path of analysis. And then we got to do the potential difference from B back to A. Now that potential difference is across resistor 2. And we are going from B to A. So our analysis from B to A, and notice our current from B to A is in the same direction. So since our current is in the same direction as our analysis path, we could say that the potential difference from B to A across resistor 2 is minus I2 R2. So this means that the potential difference from A back to A is the potential difference from A to B plus the potential difference from B to A, which is minus I1 R1 minus I2 R2 is equal to 0. Well, in the previous problem, we found that I1 was equal to the EMF of the battery over the resistance of resistance 1, and we said it was negative, right? Because our analysis direction, we know we analyzed in the wrong direction, but I'm going to stay consistent with the problem that we established. So we have I1 is equal to minus E R1. This is, and that's a minus times a minus. So let's back up a little bit. So we have to put this in parentheses, and there's a minus in front of that. And then we have a minus I2 R2 is equal to 0, and I forgot to put my R1 here. Let me back up a little bit. So that is minus current I1 times the resistance of resistor 1 minus current I2 times the resistance of resistor 2 is equal to 0. So in this first one, we have a minus times a minus is a positive. So this gives me in that first term the EMF of the battery. And then the second term is minus I2 R2. Let's go ahead and express R2 in terms of R1. Remember, R2 is twice R1, and this is equal to 0. So current I2 is equal to the EMF of the battery divided by 2R1. So notice this. Notice how we have a positive current here. So what that means is we chose the correct direction for the current through resistor 2, and now we have its value. And notice the current through resistor 2 is equal to 1/2 the current through resistor 1. And that makes sense because resistor 2, remember, is a 6 ohm resistor. Resistor 1 is a 3 ohm resistor. So if we have double the resistance, it makes sense that we would have half the current for the same potential difference. Okay, so we found current 1, we found current 2, but we're really trying to find I, the current flowing in the branch of the battery. Well, this is where Kirchhoff's law for current comes to play. Look at point A. So point A, remember, we know that the current going into point A must be equal to the current going out of point A. So in our diagram, the current going into point A is I plus the current going through resistor 2. And the current going out of point A is equal to I1. And again, this is based off of our original assumptions. Remember, we have to stay consistent for this to work out. And the reason why it'll work out, because all of the rules are such that the consistency will allow it to work out. So this means that the current in the branch of the battery is equal to the current through resistor 1 minus the current through resistor 2. But remember, the current through resistor 1 was, and I forgot to put my minus here because we're staying consistent. The current through resistor 1 is minus the EMF of the battery over the resistor of resistor 1. The current through resistor 2 is equal to, here we have a minus the EMF of the battery over 2 times the resistance of resistor 2. So when we add those two together, we get minus 3 halves the EMF of the battery over the resistance of resistor 1. So notice that current is negative. Well, it makes sense it's negative because we knew I deliberately chose the opposite direction of what the current was actually going to go in the battery. And the magnitude of the current is no problem. The current is 3/2 the EMF of the battery over the resistance of resistor 1. But the minus sign means that the current is actually opposite the direction that we assumed. So let's look at these now. And let's just redraw our circuit with the correct current directions. So in redrawing our circuit, remember, we said that let's do that again. We set that the current through resistor 1 was opposite the direction we assumed. So the current is actually down. And now we can just write that that is just the EMF over the resistance of resistor 1. The current through resistor 2, we assumed the correct direction. And that was equal to EMF over 2 times the resistance of resistor 1. And the current through the battery, we now know we chose the opposite direction to the direction that the current is actually moving. So this is I is equal to 3/2 EMF of the battery over the resistance of resistor 1. So there we have it.